Oh. Yeah, let me know when to start.
Yeah, so I think people are still drifting in a little bit. So
Okay.
just give a couple of minutes. Yeah. Okay, let me see. Prospects are in. Yeah. Oh, so Tsachik, I'm recording this talk.
That's good. But by the way, this is not mirror reflected, right? Because I see it mirror reflected, but I assume you see it good.
Yeah, so we are seeing some reflection somewhere, but I think the writing is quite visible.
Ah, so it's not focused.
No, it's focused. It's focused. It's just that there are some patches on the board which have some extra piece of light. But that's okay. It's
maybe it's better like that.
Yeah, this is good. This is good. This is really good.
Maybe I close the.
Yeah, this is very good.
I'll try something.
No, the previous one was better.
Like that?
No. Yeah, without the light is better.
Without light at all.
Yeah. That now it's good. Now it's good.
And now?
It's okay. It's all right. It's okay.
Okay. Yeah. I think Blackboard are better for Zoom than for camera than whiteboard. That's
true.
That's my experience.
Yeah. That's true. Yeah, so I think, maybe you can start now. Great pleasure to have Tsachik following up on his second talk on invariant random subgroups. And all yours, Tsachik, yeah.
Thank you. So it is a second talk, but actually it's independent of the first. So last time we spoke about invariant random subgroup, and somehow what I tried to convince you last time is that invariant random subgroup is a great tool to study lattices and maybe asymptotic invariant of lattices when the volume goes to infinity. What is an invariant random subgroup? It's a probability measure on the space of subgroup of G. So for instance, if G is a Lie group, you want to pick a subgroup. So there is a probability measure, but you want to do it in a way that it's invariant under conjugation. So basically, you're looking at a measure on the space of closed subgroup of G. And this measure is invariant under the action of G on the space by conjugation. Now, usually I'm interested in groups which are semi-simple Lie groups, so these groups are non-amenable. So when you restrict yourself to invariant measures, you lose a lot of most action of non-amenable group do not admit invariant. Okay, so if you the invariant measures are very limited, so you gain a lot of stuff that you can look at if you allow yourself to deal with non-invariant measure. So basically, the talk today, everything I say today is a joint work with Mikko Tsachik, and it's about application of non-invariant and subgroup, or more precisely, what we're looking at are stationary random subgroup. And we will add the word discrete here. So what do I mean? What do I mean by that? So, so basically, so let G be a group. And let's say mu be some probability measure on G. Maybe this mu, the probability measure on G. So it's not a hard measure, it's some measure. I will give example. And then G acts, let X be, let's say, a G space, a compact G space. So G acts on X by homeomorphism. Now, if you have a measure on X, if nu is a probability measure on X, so let's say Borel regular probability measure on X, then and G is an element in G, you can look at push forward of the action of G on nu is another probability measure of X. So the elements of G acting on X, and therefore G also acts, if you want, G acts on the space of probability measure on this of X. And the action here, if you want, is nicer. So this is also a compact space, but it's also a closed convex subset of the Banach space, and X acts by a fine action, a fine homomorphism. And then when you can look at the orbit of a measure, and you can average over the orbit of over mu, and you say that nu is stationary. With respect to mu, if you want, the convolution of mu and nu is equal to nu. Or if you want, the integral of G star nu d mu G equals nu. It is the same thing. So then this is the notion of nu stationary, and the point is now for every group action on a space, there are mu stationary. This is just because of the amenability of z or n, of the integer. So by the maybe Kakutani fixed point theorem, you can find so for any action. So this says that there are much more stationary measures than invariant measures. Of course, every G invariant measure is also stationary, but there are much more stationary measures than invariant measure. And one way to get a measure like that is to consider a random walk. So example, how do you get a stationary measure? Example is a limit of random walk. So if you want, let say nu be any measure on X, and now you can define for any n, you define nu n to be the Cesaro average of the sum I goes from 1 to n of mu I convolution nu, where this is the ith power convolution of mu with itself, and this is again a probability measure inside of X, and the space of probability measure is a weak star compact, so you can take a limit of this random walk. So let nu infinity be a weak star limit, then nu infinity is stationary. Nu infinity is nu infinity. This weak star limit is not necessarily unique. Usually it's not unique. And of course, it depends. You prove its existence by rely on the axiom of choice. So the limit is not unique, but there is a limit because of compactness, and the limit is stationary. So that's one way. So that's okay. That's very, very general, very, very basic, and I'm sure most of you know this stuff. And now the idea of me and Miko, we wanted to study a specific problem about discrete subgroup of semi-simple Lie group, which was a conjecture of Margulis. And let me first state the theorem and then describe a proof. So the theorem the other one was better. So let me restrict to simple Lie group of rank at least 2. Although the theorem applies to semi-simple Lie group, but the formulation is a bit more detailed. So let G be connected simple Lie group of real rank at least 2. So if you want, I consider SL3R, but I don't consider SL2R. SLNR for n at least 3, or if you want SOPQ, where both P and Q are bigger than 2, and so on. There is a list, a full list of all simple Lie group, and the rank 1 corresponds to negative curvature. The higher rank corresponds to more rigid group for which the superrigidity theorem apply, and the normal subgroup theorem, and so they're much more rigid. They have property T. So I consider such a group. Let X, okay, I use X, let S be the symmetric space. Be the symmetric space. So K is the maximal compact subgroup. I choose the maximal compact subgroup, and then G mod K is the Riemannian symmetric space corresponding to X, to G. It's a very nice space canonically associated to G. For instance, if G is SL3R, this is a 5-dimensional space. If G is SL2R, by the way, this space is H2, the hyperbolic plane. If G is SL2C, this is H3, the hyperbolic space. But I consider a high rank group like SL3R, then it's a 5-dimensional space, which is, if you want, many flat Euclidean planes inside it. So it has a Riemannian structure induced by the killing form of G, and G acts on it. G is almost the group of isometries, actually the connected component of the group of isometries of this symmetric space. Okay. Let gamma inside G be a discrete group of infinite covolume, so which is not a lattice. A discrete group. Then for a discrete group, you have a lot, every discrete group in G corresponds to a locally S manifold with corresponding, okay, let M be S mod gamma. S mod gamma, or if you want, G mod K mod gamma, it's the same thing. So this is an S manifold. So it means that it's a manifold whose universal cover is S, and it's locally isometric to S. Gamma acts discretely or properly on S, and the quotient is a manifold. Actually, it's not necessarily a manifold, it can be an orbifold. There could be some ramified points, which has a non-trivial finite stabilizer, but okay, so let's M be the corresponding S manifold. S orbifold. Okay, so this is just assumption. So there is a very rich theory about such orbifolds when they have finite volume. Then gamma is a lattice, and we know a lot. We know superrigidity, and we know many things about such manifold or orbifold of finite volume. But we know much less. The theory is much less evolved for general S orbifold, and our theory is about such orbifold. So if gamma is not a lattice, so if the volume of M is infinite, then the injectivity radius is infinite. So I will write it like this. Then for every R, there is a point in M such that the R pole around this point is contractible. The pole around P of radius R is contractible, or if you want, is isometric to an R ball in the universal cover. The universal cover is homogeneous. All R balls are translated of one another. So the ball of radius RP, the ball of radius R around P is contractible. It's the same thing as saying that it's isometric to a ball in S. Because of non-positive curvature, it's the same thing. So I just say it's contractible. That's the theorem. So the ball around R is contractible. The ball around P of radius R is contractible. Let me say it in a few more words. So that's the theorem. Let me just write it differently. So given such M, we denote by given R a positive number, you denote by M greater or equal to R the R thick part. So it's the set of all points inside M such that the injectivity radius at P is at least R, where injectivity radius means the supermum over all R, the supermum over the radius that the ball is contractible. If you want another way to say it, the injectivity radius at a point is half of the length of the shortest closed loop, which is homotopically non-trivial. So that's injectivity radius. So the picture, again, if you have a manifold, and let's say R is like that. So this is M greater or equal to R. It is not connected. It has two components in this picture. Usually, okay. It's not necessarily connected. But for finite volume manifold of dimension at least 3, it happened to be connected, at least for smaller. Yeah, okay. So basically, the theorem says that if the volume of M is infinite, is not finite, then for every R, there is a thick part. This is not empty. That's a theorem. And the idea of the proof is to apply random walk. We want to say, to show that the thick part is not empty, and the way we do it is by doing random walk on this infinite volume manifold and looking at the function, which is the injectivity radius, and shows that with the probability go to 1, you will be eventually in the R thick part. So for every R, so we actually prove a stronger theorem, which is as follows. So we actually prove the following theorem. Let's mu be in our probability measure. Okay, I will not write it yet. I will change to a different language. But basically, with respect to some mu, okay, let me. Yeah, we show the following. So we show that the mu random walk on M starting from any point. Eventually, and most of the time, in our thick part. And this is true for every R. So in particular, the R thick part is non-empty. But let me formulate it mathematically more precisely by looking not on M, but on the subspace that we looked last week. We looked at the Tsachik space of closed subgroup of G. And inside that space, we look at this is a compact space. And inside that space, we look at the open subset of discrete subgroup. And again, I want to look at that. So I didn't tell you what is exactly the measure mu that I'm working with. I will tell you in a maximal compact subgroup of G, which is K, and I take the Haar measure on K, convolution with Dirac measure on some specific element, and again, Haar measure on K. So this is the Haar, normalized Haar measure on K, on the compact subgroup. So I take, so this is a probability measure on G, which is by K invariant, and this is a Dirac measure supported on a single element, and this element, well,
there's a question from the audience.
Yeah, if there is a question, don't write it, but just ask it.
Yeah, so so this question is, I mean, does it say something about Benjamin-Schramm convergence? I mean, take a random point and look at the ball around it. Does it say anything?
You take a random point. So, yeah, I mean, it says something about. Okay, let me try to say it in this way. In this Benjamin-Schramm. Benjamin-Schramm is about pointed measured pointed space, and now when you have measure on manifold, So it says I can formulate it in the language of Benjamin-Schramm. Let me. I will do it soon. Okay. So let A be an element which is very contracting. Let's say a semi-simple element, like a point in the K decomposition, which is very contracting. When restricted to the unipotent radical of some minimal parabolic on U, which is the radical, unipotent radical of P, and this is some minimal parabolic. What I say now is maybe technical. Let me just write it on for SLN R, or SL3R. For SL3R, you can take A to be the following matrix: 100, 1, 1 over 100. So that's the element we're looking at, and I look at Dirac measure on this element, and then I multiply it from left and right, convolution with the Haar measure on K, and this will give me a nice measure on G. And from now on, I will work with this measure mu. Because, yeah, expectedly, what I'm going to say will be true for other measures as well, but I know we know to prove it for such measures, but not for general measures. So what is the theorem? So consider, so here is the theorem. Let me just recall you the notation from last week. Sub G is the space of all closed subgroup of G. This is a compact space with respect to the Chabati topology. There is a topology here called Chabuti topology, and this is a compact space, and G actually by conjugation. And last week we looked at invariant measure on the space. These are IRS. Inside this space, we have the open subset of discrete subgroup. It's not anymore compact. A limit of discrete group can be non-discrete, can be connected. It's restrictive. The limit cannot be anything. You cannot approach G by discrete group. If you approach something, it must have an important connected component, and so on. But still, this is not a compact, or this is not a closed subset. Now, I can consider a random walk on the space sub G, on the space of closed subgroup. G acts on the space, it's a compact space, and then I can start with any probability measure on sub G and do the random walk, the convolution, and go to infinity and get a stationary limit. And the proof, the result that we are getting is the following. So again, so let G be simple, of rank is 2. It's not true otherwise. Let's start with lambda inside the space of discrete subgroup. So it's just a discrete subgroup of G, such that the volume of G mod lambda is infinite. Consider, let nu n be the Chazal average of the, I convolve with mu I times the Dirac measure on this discrete group. So now these are all measures, these are all probability measures. These are all probability measures on the space of closed subgroup of G. And I can take limits of them and study with the stationary limit. This would be a mu stationary group. And what we prove is the following. Then this converge to the Dirac measure on the trivial group. So if you want, for every discrete group, gamma inside G, so these are all probability measures supported on discrete group. the limit, it's also discrete. That's what we prove, but it's not obvious. So the first step in the proof is to prove that the limit is discrete. It's supported on discrete group, because the space of discrete group is not compact anymore. So somehow you can imagine that certain situation, you start with measures supported on discrete group, but then you convolve it, and in a limit it's pushed to measures supported on non-discrete group. But here it's not happened, so the limit will be supported on discrete group, and we can actually analyze it and show that it's Dirac on the trivial group. But what does it mean in the terms of Benjamini-Schramm? So for every discrete group, gamma in G, you can look at S mod gamma. S was G mod K, S is the symmetric space. S mod gamma is an S manifold. And there is a special point in S mod gamma because we fix the compact subgroup K. So when we look at S mod gamma, is G mod K mod gamma, there is a special point. So for every gamma in G, we get a point in the Gromov-Hausdorff space, or associated to S, which means just a S manifold and a point, as a pointed S manifold. And now we have probability measure, nu n is a probability measure on the space of discrete subgroup of G. So if you pick a group at random, you get a point in the Gromov-Hausdorff space at random. And so you get a measure on the Gromov-Hausdorff space, which is a point in the Benjamini-Schramm space. And now you can, so this measure nu n corresponds to point in the Benjamini-Schramm space, and the fact that it's converged to this exactly tell you that the limit of the Benjamini-Schramm limit of will be the symmetric space. If you translate what is written here to the language of Benjamini-Schramm on pointed S manifold, you say that we get that these pointed S manifold converge to the universal subgroup. Okay, so that's maybe answer the question that was asked before. Ask me more question if you have. I want, before going a bit to the proof, I want to say application, because one way to look at this result, I like to think of it as a geometric interpretation of Margulis normal subgroup theorem. And actually, it implies Margulis normal subgroup theorem, and it's much stronger than Margulis normal subgroup theorem. So let me give you an example that demonstrate that this is not true in rank 1, because Margulis normal subgroup theorem failed in rank 1. So here is the example. So let now G be rank 1 simple group. Rank 1. Like SON1 or SUN1 or SPN1. So it's a group of isometries of a symmetric space of rank 1. Let gamma in G be a uniform lattice. Uniform means co-compact. It means that the corresponding S manifold corresponding to gamma, this means that S mod gamma is compact. That's mean uniform. Now, symmetric space now is rank 1, symmetric space, so it's negative curvature. And uniform lattice is quasi-isometric to the symmetric space, so it's a Gromov hyperbolic group. We know that in Gromov hyperbolic group, there are many, many normal subgroups. So in particular, there is a normal subgroup of infinite index. Let lambda be non-trivial normal subgroup of gamma of infinite index. So the index so lambda is exactly the type of group that we looked before. It's a discrete subgroup of G of infinite covolume. But I know more about it. I know that it's contained in the lattice and it's normal there. Then the injectivity radius, the manifold M, which is S mod lambda, S is G mod K. So G mod K mod lambda has infinite volume, but bounded injectivity radius. So the injectivity radius here is bounded. And I leave it as an exercise. You can look in our paper, we give a few lines explanation, but it's really an exercise to see that if you know just from the fact that it's non-trivial and it's because gamma is a compact fundamental domain and lambda is normal in gamma, you can show that the injectivity radius here is bounded. So this example, such examples do not exist in higher rank because of Margulis normal subgroup theorem. Margulis normal subgroup theorem says that if G has rank at least 2, then every lattice is just infinite. So it means that every quotient, every normal subgroup of a lattice, it's either a central or of finite index. You don't have non-trivial normal subgroup. Suppose G is center free. Usually one allows finite center, but just for the formulation, suppose G is center free. So if gamma is a co-compact lattice in G, every normal subgroup of gamma is either trivial or of finite index. So that's a normal subgroup theorem. And you see that in view of this example, it's a consequence of our theorem. So our theorem is about arbitrarily discrete group. It's not just about group that sits inside lattices, but it's in particular when you apply it to normal subgroup of lattices, you get again the Margulis normal subgroup theorem. Yeah. Now let me say a bit about. I said already that we're going to use stationary, the proof use stationary, the theory of stationary random subgroup. I like to think of the proof as a 3 steps proof. So again, so let's consider this, so about the proof. So again, I recall that mu n as written above, but let me write them again. Mu n is the Chazaro average. I start with some lambda, which is a discrete subgroup of infinite covolume, and I look at the Dirac mass on lambda, and then I do this. And mu was the probability measure that were described here before. Mu is the fixed probability measure, which is R on K, Dirac on some element which is very, very contracting, very restricted to unipotent radical of parabolic. So I take by K invariant measure. Our proof relies on Neveu-Zimmer theory, or there is several papers. Okay, there are 2 fantastic papers of Amos Neveu and Bob Zimmer. The first, I think, published in 1999, and the second in 2002. about some extension of Margulis factor theorem, and we apply their theory. Now, they assumed all the time that they work with smooth measure. Well, this is not smooth, but actually you don't really need smoothness of this measure mu. What you need is some knowledge about the Poisson boundary associated to mu. And the Poisson boundary of such a measure is, okay, the Poisson boundary is always G mod P, but it's G mod P, you know that the measure on G mod P associated to this measure mu is the unique K-invariant measure, the Haar measure on G mod P, and this is good enough for all that we need. So, okay, let's go back here. So we have this series of measures. So step one, so and let nu infinity be a weak star limit. So there is a weak star limit by compactness. Banach-Halaouglo theorem says that the space of probability measure on a compact space, and the compact space that I'm looking at is the space of all closed subgroups of G. The space of probability measure is weak star compact. Now, so there is a weak star limit, maybe there is more than one. So the first step of the is I have 15 minutes, so I just first tell you what are the steps. The step one, I like to call discreteness. And it means that nu infinity is supported on the open set. Okay, the support of a measure is a closed set, but let me still say it is supported on the open set of discrete subgroup, which means that nu infinity of the space of discrete subgroup of G, it's an open subset, is 1. That's the first step. Do that. Step 2, which is a stiff, I call stiffness. I mean, it is called stiffness. It means that stationary measures on the space of discrete subgroup are invariant. Stationary measure on the space of discrete. It's not true in general. There are stationary measures on the space of closed subgroup of G, which are non-invariant. For instance, the stationary measure on G mod P gives you a stationary measure on the conjugacy class of P, and it's not invariant. But if you are stationary and discrete stationary measure on the space of discrete, or if you want a short, I like to say discrete stationary measure, discrete SRS are IRS. That's how I like to say it. So if you are both discrete and stationary random subgroup, then you are invariant random subgroups. And the last step is rigidity. Showing that IRS are applying the theory of IRS. So here, in the last step, we apply the Stuck-Zimmer theory or the Stuck-Zimmer. The last step we use Stuck-Zimmer. In this step we use Neveu-Zimmer. In step 2 we use Neveu-Zimmer. In step 3 we use Stuck-Zimmer. By the way, also Stuck-Zimmer relies on the work of Neveu-Zimmer because there was a gap in the original paper of Stuck and Zimmer. No, not in the paper of Stuck and Zimmer. There was a gap in an earlier paper of Zimmer, which used in Stuck-Zimmer work, and later this gap was filled in the work of Neveu and Zimmer. So step 2 is relying on Neveu-Zimmer. That's the main part of the paper. Step 3 relies on Stuck-Zimmer. Step 1 uses a recent work by Ariel Levy, myself, and Margulis. So in order to prove that the limit is discrete, we rely on a recent work with Aryeh Levitt and Grisha Margulis. So maybe I have now 10 minutes, so I can tell you either one of the steps, for instance, why the limit is discrete, or I can tell you a generalization of this theorem to the context of semi-simple group, which are not simple, so there are more than one factor. So let me tell you a bit about this, about the discreteness. So we have a sequence of measures supported on discrete group, and we want to show that the limit measure is also supported on discrete group. The idea to do that is to use what is called to show that you can cook a Margulis function which is more or less the injectivity radius. So let me be more precise. So let G be the Lie algebra, and let this be a norm, any norm on G, such that the exponential map restricted to the unit ball where the norm is less than 1 is a diffeomorphism. Now, using that, I define the discreteness function. Set O is a function from the space of discrete subgroup of G to the real number, the positive real, and this is called the discreteness function. So rho of a group will be the supermove over R.
Could you use a different pen? The pen is.
Yeah, sorry. So I'm defining a function on discrete group. For every discrete group, I want to say some parameter which tell me what is the discreteness radius. How discrete is it's measure how discrete is this group. The larger this parameter will be, the more discrete is the group. Is the supermum over all R, but up to 1. Just consider R smaller than 1, such that the exponent of the unit of the ball in the Lie algebra of radius R intersect the discrete group trivially. This is it's measured how discrete is your group. But as you see, it's only good for small injectivity radius. So it doesn't distinguish between group which intersect this unit ball trivially. So this is the injectivity radius of lambda, if you want. Or it's related, sorry, this is the discreteness of lambda. And now the theorem that we prove in a different paper. With Arya Levitt and Margulis, is that there exists delta positive and C also positive but smaller than 1. So delta is very small, C is not so small, but is smaller than 1, and B, any number, also positive, but B is less important, such that rho to the minus delta, if I convolve it with mu, it will be smaller than C times rho to the minus delta plus B. That's if you want, the key inequality that we proved in this work. This has many applications. In the work with Levitt and Margulis, we got a specific estimate. We wanted concrete estimate for delta and as well as C and B. Because we wanted some application about, in particular, we wanted to get an effective version of the celebrated Margulis theorem about discrete subgroup of semi-simple group. So we wanted an effective version. Of course, this delta and C and B depends on the choice of the element A. In the measure mu, there is a choice of an element A, and as long as A is big enough, it's contracting well enough, this works, but the actual constant depends on A. Now, once you have such a property, this is called such an inequality for people in homogeneous dynamics, I think such an equality, we say that rho to the minus delta is a Margulis function. So yeah, so that's the and once you have this, you can prove the following. So you can prove theorem 1, the theorem that is in step 1 is actually a few lines after you know this. So this implies the following theorem, theorem 1, that is what is written there. So every weak star limit is supported. Okay, every weak star limit of nu n is supported on this discrete group. So if you take the limit and you take a random group, the probability 1 is discrete. So although the proof is few lines, I will not write it. Again, you can look at the paper. The idea of that step is already in the work of Esky and Margulis, which they study completely different questions. They study random walk on arithmetic manifold, but again, they use some similar function and prove the similar inequality and obtain similar consequence. So for this step, the idea is there. Yeah, that's about the first, a bit about the first step. The second step, I could dedicate several talks to the second step, the stiffness result, which relies on the Vaux-Zimmer work. But now it's, I think it's the end of the talk, so yeah, it's maybe you can show yourself or ask question. Yeah.
Okay, thank you very much, Tsachik. That was wonderful. Yeah, so just if anybody has any questions, please unmute yourself and directly ask Tsachik. Yeah. Yeah. So so there are a couple of questions. One, I mean, what exactly is it that you are using about this particular measure? I mean, that Dirac, say, convolved on both sides with the Haar. I mean, is it some moment conditions or what? I mean, or what exactly is being used about that particular probability measure?
So the proof of this inequality is actually very similar to the original proof of Kashdan-Margulis theorem. Kashdan-Margulis proved that for every semi-simple Lie group, there is an identity neighborhood such that every discrete group you can conjugate to intersect this trivially. To intersect, that's Kashdan-Margulis theorem. Now, we wanted the original motivation of the work with Ariel Levitt and Margulis was to get effective version of that, also stronger version, not just effective, but it also works in different contexts, like say positive characteristic group and so on. But we wanted to get effective version, and for that we proved such inequality. But we rely on the same thing that they relied. We do it more carefully. So instead of 3 pages, our paper is maybe 50 or 40 pages. But we relied on this Zassenhaus neighborhood. We rely on the fact that when you conjugate, so it's not a moment condition. It's not a moment condition. It's just particularly how you expand nilpotent Lie groups when you act on them by conjugation of semi-simple element or from the Cartan decomposition. So yeah, so basically that's what we use.
Thank you, thank you. So one more question. This is about the step 2. How general is this? I mean, what is the hypothesis? What is G here? I mean, say even for simple groups, is it for arbitrary simple groups or is it only for higher rank?
Yeah, that's excellent question. Let me state the theorem, and then we proved the following theorem. In step 2, we proved the following theorem. We need some irreducibility in the rank 1 factors, and we really need that. So let me say so. So let G be a semi-simple Lie group. Now, by the way, so the precise assumption about mu that we use is the specific formulation of mu is just for step 1. For step 2, that's much more general. For any mu, any sufficiently nice mu, we have let, I don't know if the color is good enough, let nu be a probability measure on the space of, let's say, a discrete subgroup of G, such that nu almost surely the intersection with every rank 1 factor is driven.
I see. Okay, thank you. Yeah.
Actually, you don't really need trivial. It's enough to assume that it's not Zariski dense. But let's assume trivial. The intersection with every rank 1 factor is small. Then okay, we assume mu is stationary. The assumption that mu is stationary with respect to almost any measure on G will work for that. Then nu is an iris. Invariant. That's the theorem. Now, after we proved that, we thought that it's also true in rank 1. By some different methods, we thought, okay, in rank 1 we cannot apply Neveu-Zimmer theory, but maybe we can use some ideas from the proof of Ratner theorem or so on, but it doesn't work, and it's not true. We realized that there are counterexamples. For rank 1 group, you can construct stationary random subgroup which are non-invariant and not even close to be invariant. You can show that every group in the support of that measure is not containing the support of every IRS and so on. So in rank 1, the picture of stationary random subgroup is more complicated. So you don't have this stiffness.
Fantastic. Okay, great. Thanks so much. Thank you.
Thank you.
Yeah.
So just if you can send me the recording again, I'll be happy. Like last week.
Sure. Yeah. Thanks a lot, Tsachik. That was wonderful. Okay.
Yeah, bye. Thank you. Hope to see you sometimes for real.
Absolutely. Yeah.
Yeah.
Okay.
Bye-bye. Thank you. Bye.